we're now moving on to section 2.6, which talks about a different type of limit. It's called the limit at infinity, and that deals with the question of when the magnitude of x becomes very large. In other words, as x goes towards positive or negative infinity, what is happening to the y values? So let's try an example here. It says to evaluate x goes to infinity of x squared minus x. So what that means is x is getting very large without bound. Now here we can't do direct substitution because infinity is not a number. That means it's never in the domain of any function, so we can't substitute infinity into this function. Now, I will often see students doing direct substitution and getting something like this. They'll say, oh, infinity squared is infinity, and so infinity minus infinity is 0. This is actually wrong. I mean, there are many problems. As I said before, you can't do direct substitution first of all, and second of all, infinity minus infinity might not be 0. It's actually an indeterminate form, which we will talk more about later in this course. But for now, just know that you can't make such an argument. So what do we do then? How do we evaluate this limit if we can't do direct substitution? Well, we'll have to go back to what we used to do, which was by graphing it. And the general shape will be a parabola. It's a polynomial of degree 2. And since the coefficient of x squared is positive, it's a parabola that opens up. So maybe it looks something like this. Let's write that down. We have a parabola that opens up. And no matter where this is located on the xy plane, as you keep going towards the right along the curve, you're going to go towards y is equal to infinity. So that means this limit as x goes to infinity of x squared minus x is infinity. Let's try another one that's a little more complicated. So it's asking you to find the limit as x goes to infinity of this rational function. Drawing this is not going to be easy, so let's not do that. Now, I have a caution here again, and I will often see students say, well, the numerator is going to go towards infinity because it's a parabola that points up, just like this one. And the denominator is also going to go to infinity for the same reason. So then we'll have infinity over infinity, and that's 1. This is also wrong. Infinity over infinity is actually an indeterminate form. It's not going to be 1. They won't have the effect of canceling out or anything like that. So here's what we're going to do. Whenever you have a rational function like this and x is going towards infinity, you can always use this rule here. You're going to divide the numerator and the denominator by x to the n, where n is the highest power of x that occurs in the denominator. So since the highest power that occurs in the denominator is 2, that means you're going to divide the numerator and the denominator by x squared. Let's see what we get then. We have limit as x goes to infinity of, now distribute the division. So we have 3x squared over x squared is 3, minus x over x squared is 1 over x, minus 2 over x squared, divided by 5 plus 4 over x plus 1 over x squared. Now, we still can't do direct substitution because infinity is not in the domain of any function. So again, we're going to go back to the basics. We're going to use the limit laws as well as the graph of these functions. There are only 2 different types of graphs that we need to look at in this case. The graph of 1 over x, which will give us the answer for this one and this one, and the graph of 1 over x squared, which will give us the answer for this and this. And the limit law just distributing all the limits inside, which I will not write down. So the graph of 1 over x, we all know, looks like this. There is a horizontal asymptote at y is 0, and 1 over x squared looks like this. There is a horizontal asymptote at y is 0 as well. All right, so examining these graphs, again, we're going to evaluate these limits all separately using the limit law. Let's figure out what 1 over x goes to as x goes to infinity. Well, you're going towards the right forever then along this curve, and it's going to get closer and closer to the horizontal asymptote, which is at 0. So this goes to 0. We'll put an arrow to say it's going to 0. And that means this is also going to 0 because 4 over x looks very much like this, except it's stretched vertically by a factor of 4. That doesn't change the behavior as x goes to infinity. So it also goes to 0. Now let's look at 1 over x squared as x goes to infinity. Again, that means you're going towards the right forever along the curve. And again, you're approaching 0 because there's a horizontal asymptote there. Then similarly with 2 over x squared, that goes to 0 because, again, 2 just vertically stretches this graph without affecting the position of the horizontal asymptote. So we can conclude that since all of these are just going towards 0, limit as x goes to infinity of this thing is just 3 over 5. Now, this is a perfectly reasonable way to answer this question, but there is actually a shortcut that you might want to think about using. This only works if you have a limit at infinity, positive or negative infinity, and you have a numerator and a denominator. Then only consider the terms with the highest power what we will call the dominant terms in the numerator and the denominator, and then ignore all the other terms. That will simplify your limit, and then it'll become easy to answer. So here's what I mean. We have the same limit as above, and let's follow this shortcut by only keeping the terms with the highest power in the numerator and the denominator, and then ignoring everything else. This is the term with the highest power in the numerator. You have to keep the coefficient as well. And this is the term with the highest power in the denominator. Now ignore everything else. And what we're saying then is that this limit is the same as the limit as x goes to infinity of 3x squared over 5x squared. Now we can cancel out the x squareds, and limit as x goes to infinity of a constant is just that constant, because this is just a horizontal line, so as x goes to infinity, this will always be the y value. So we got the same answer as above, but this was much faster. It turns out that this is the graph of this function, and as you can see, as x goes towards infinity, the y value is going towards some constant, and it turns out that constant is 3 over 5. And hopefully you can all recognize that this is what we call a horizontal asymptote. So figuring out the limit at infinity helps us figure out the location of the horizontal asymptote. So here's a formal definition of what a horizontal asymptote is in terms of limits. The line y is equal to L, where L is some real number, is called a horizontal asymptote of y is equal to f of x if either the limit as x goes to positive infinity of f of x is L, or the limit as x goes to negative infinity of f of x is L. Only one of these has to be true in order for there to be a horizontal asymptote at y is L. So what this is saying is as x gets really, really large, so as you go along the curve towards the right forever, the y value is going towards some number L. Here are 3 examples of that happening. So the y value is getting closer and closer to L as y goes to positive infinity in this case. Same here and here. Now, you can cross the horizontal asymptote. There's no law against that. The only condition is either this has to be satisfied or this. Notice that you're crossing the horizontal asymptote, in fact, infinitely many times in this case, and that is perfectly fine. It's still a horizontal asymptote because it satisfies this. Now, what this is saying is you're going towards the left forever along the curve. And as you're doing that, if your y value is going towards L, then that means there is a horizontal asymptote at L. And here are two examples of that. As you keep going towards the left, the y value is getting closer and closer to L in both cases. It turns out that the limit laws can also be used to limits at infinity, which is very helpful for us. In fact, I use a limit law without mentioning that earlier. All right, so let's try this. It's asking you to find all the horizontal asymptotes of the graph of this. Okay, so that means you have to evaluate two limits. Limit as x goes to positive infinity, and the limit as x goes to negative infinity. The reason is that there might be two different horizontal asymptotes. You might be going towards one number as you go towards x's infinity, and a different number as x goes to negative infinity. And you won't catch them both unless you do both of these. So there are two different ways of doing this. I'll use one way for this first limit and then a different way for the second. So what we did in the beginning was use the rule here. So divide the numerator and the denominator by x to the n, where n is the highest power of x that occurs in the denominator. Let's try it that way. So the highest power of x that occurs in the denominator is x. Let's divide everything by x then. So we have square root of 2x squared plus 1 over 3x minus 5. Divide the top and bottom by x. Then we get the limit as x goes to infinity of, now the square root, I'm going to bring the x inside. When x goes inside the square root, it'll become x squared. And the denominator is simpler, it's just 3 minus 5 over x. Now let's simplify what's under the square root. So we have the limit as x goes to infinity, square root of 2 plus 1 over x squared, divided by 3 minus 5 over x. Now, as we saw earlier, 1 over x squared goes to 0 as x goes to infinity. And 5 over x also goes to 0 as x goes to infinity. So we have the limit as x goes to infinity of root 2 over 3, which is just root 2 over 3. So we figured out that as x gets really, really large, the y value is going towards root 2 over 3. Since this is a real number, that means there is a horizontal asymptote at y is equal to this number. Again, there could be another horizontal asymptote, so let's check if that is the case by using this limit as x goes to minus infinity. Now I'm going to use that shortcut, which is here. Just take the dominant terms in the numerator and denominator only, ignore all the other terms, and then evaluate that limit. The dominant term in the numerator, in other words, the term with the highest power in the numerator, is this thing. You have to take the square root as well, so it's square root of 2x squared. And the dominant term, or the term with the highest power in the denominator, is 3x, so we keep that one. And what we're left with is the limit as x goes to minus infinity of root 2x squared over 3x. Now this one's actually a little bit tricky. Because x is going towards negative infinity, square root of x squared is not x. Square root of a squared is not a, it's absolute value of a. right? For example, square root of negative 2 squared is square root of 4, which is 2, not negative 2. The negative disappeared. All right, so we have limit as x goes to minus infinity of root 2 times square root of x squared is absolute value of x divided by 3x. We need to simplify this function before we evaluate this limit. And to do that, what we can do is say absolute value of x is negative x. Because x is negative, absolute value of x is the same as negative x. So we have limit as x goes to minus infinity, root 2 times negative x divided by 3x. And the x's cancel out, and you're doing a limit as x goes to negative infinity of minus root 2 over 3, which is minus root 2 over 3. So actually there is another horizontal asymptote at y is minus root 2 over 3. As x gets really, really small, the y value is going towards minus root 2 over 3. Turns out here's the graph of the function here. Notice that as x gets larger and larger, the y value is going towards one number, which happens to be root 2 over 3. And as x gets really, really small, the y value is going towards something else. It in fact goes towards minus root 2 over 3. Alright, so in summary, there are two horizontal asymptotes with equations y is root 2 over 3 and y is minus root 2 over 3. That's the end of 2.6. Homework questions for you to do from the textbook, and thanks for listening.